Hello, so we're going to see a new kind of transformation, which is called the Laplace transform. So it's also an integral transform, quite similar to the Fourier transform, and it's a tool that is mostly used to solve differential equations, because when you apply Laplace transform on a differential equation, you make it an algebraic equation, which is much simpler to solve. Okay, so basically, we're going to see the properties of this transformation. That's going to lead us to build some tables similar to this kind of thing of Laplace transform. And the good thing about this transform is that it's reversible. So if you apply the Laplace transform, do some work on the transforms, then you can get back again on your original functions. Okay, so that was all invented by Pierre-Simon Laplace around the end of the 18th century. So that was a bit before Fourier transform. So let's have a look at what we have. Um, Maybe first we can just state things. Fourier transform, we use to denote that with a calligraphic capital F. So we apply it to some function f, and usually we use the variable xi. And what did we have? We have that xi was a real variable actually, and f hat of xi, if you define this as being f hat xi, is actually complex function, right? But of a real value, of a real variable. Okay, in Laplace transform, usually we're going to have all the capital L, calligraphic L notation applied to a function f of the variable. So usually in the Anglo-Saxon world, we were going to use the variable s. If you refer to French mathematics literature, you will often use the variable z, but whatever, it's just going to be the same. What's different here is that s or z belong to c, and we're going to have that L of s. The Laplace transform of your function is also a complex function. Okay, so let's begin by giving the formula, the definition. So usually we begin with a function f of the variable, whatever, let's use t, which is very common. T from belongs to R plus. Okay, and so we've got, well, f of t is going to be, well, if you want to define f for t negative, we can put that f of t is equal to 0. If t belongs to negative infinity 0, and you will see that we need that in order to get some convergence of the definition. So what do we have? We have that the Laplace transform of this function as a variable of s is given by the integral from 0 to plus infinity of f of t e minus s times t. Okay, so the variable s appears here. So you see, it's quite similar to the Fourier transform, but well, s is just supposed to be a complex number. We didn't say it was just I 2 pi I something. So it's supposed to be a complex number. And in order for these to have convergence, well, we need several things. First of all, we needed, well, if you say that f is 0 from negative infinity to 0, you don't care about the integral being defined only on R plus, because then it's going to cancel. Right. So we assume, what are the assumptions for convergence? Sorry about this. Let's go back to my function. So we assume f grows at most as an exponential. Why? Just in order so that, so what does that mean? It means that there exists some value such that for all t in R, or at least for t big enough, because what's happening for small t doesn't matter in terms of convergence, so that f is smaller than m exponential at for some a. Okay, it has at most some exponential growth, so that we get that in the end the limit as t tends to infinity of f of t times e minus zt in terms of modulus tends to 0. Okay, all right. Um, and then we have, of course, that would you will say that wait a minute, that's going to be depending on the value of the a that I've chosen. So well, actually we will have to define what's called the convergence domain, and that is we're going to have that this limit at infinity is true if the real value of, sorry, I've used the z variable, if the real value of my s variable is greater than a, so that the exponential minus real value of s times t wins over the exponential of capital A times t. Okay, so we also see that we're going to need that notion of convergence domain. Okay, so let's do our first example. So let's choose the Heaviside function. So, or called the unit step function. So h of t is just the indicator function of the positive numbers, right? So this is the one. So let's do the Laplace transform of this function. It's going to be the integral between, well, that's always 0 plus infinity times 1 of 0 plus infinity. So basically that's not going to change anything. Exponential minus st dt. Okay, which is of course integral from 0 to plus infinity. My one function is just, well, transparent for that. E minus st dt. Okay, so now we need to do this calculation. Well, that's an exponential of a complex number. We haven't really worked on that. So either you can, well, we can do it at least once. We can just split that into integral between 0 and plus infinity e minus real part of s times t plus times, sorry, e minus I imaginary part of s times t dt. Okay, so now in terms of convergence, we see that this is going to be, well, in terms of convergence, I have that the modulus of all that is going to be equal to the modulus of only the exponential minus real part s times t, okay, and which is itself going to be a an integrable function, so that could be used as dominating function, but this itself is integrable. Okay, I remind you, it's just because the modulus of that imaginary part has modulus of 1. Okay, that exponential of the I stuff as modulus of 1. Okay, so we said that this is going to be integrable if and only if we need that the real part of s is strictly greater than 0, so that I get the exponential of a negative number in the end, right? So what do we get here? That the convergence domain is going to be all the s in C such that their real part is strictly positive. Okay, so half of the complex plane. And now let's perform the integration. Actually, we don't need to split that for the integration. We just get So we divide by 1 over s exponential minus s times t between 0 and plus infinity. And so what do we get? At plus infinity, that's exponential minus s times t, which I remind you, so maybe we can do it once on the side. Exponential minus st as t tends to infinity. What is that? So you're all tempted to say it's 0, but maybe we need, as s is complex, we need just just one step to see it once. It's just going to be e minus real value of s times t times e minus I imaginary value of s times t. And so what do we have in terms of modulus? That's modulus equal to 1, and anywhere that is going to be bounded, and this anyway is going to go to 0 as t tends to infinity if we said that the real value of s was strictly greater than 0. So that's 0 at infinity. Okay, so that's going to be 0 at infinity. So that in the end, when we solve that, that's the value at infinity is 0. Value in 0 is minus 1 over s exponential of 0. So that's just 1 over s. Okay, so that's our first result. The Laplace transform of the Heaviside unit step function is 1 over s. Okay, and actually out of that one, we're going to see a lot of properties that are going to help us build the Laplace transforms for many other functions. Well, before we go on with the usual properties of the Laplace transform, let's just have a very quick look at its relation to the Fourier transform. So let me remind you that f hat of psi is defined as the integral on R of f of t e minus 2I pi psi t dt. Okay, if I choose the variable t, and that's actually going to be the Laplace transform of this function f, if ever it's, well, we still need to discuss its convergence domain, applied to minus 2I pi psi instead of applying it to any complex number s. Okay, so what do we get? Indeed, because when we do the Laplace transform of f of t applied to s, it's given as the integral from 0 to plus infinity f of t e minus at e minus I bt dt. So you can also see that as being the Fourier, well, conversely, as the Fourier transform of the function. Well, I have h of t because the integral is only from 0 to plus infinity. I have my function defined as e minus at times f of t, and the variable now is going to be b over 2 pi. Well, if b was the imaginary part of s, okay, with s is equal to a plus ib. So what can we get from that? That the Laplace transform for the real value of z is equal to 0. So when I is equal to 0, that means that that exponential is equal to 0. And if ever your function was only defined on positive numbers, well, if you have your h of t in front of that, that's going to take the same values. Well, it's just going to be a scaling of the same values as your Fourier transform. Okay, and so what we can say is that along the line, the line where of the complex plane where the real value of my complex number is constant, I've got actually the Fourier transform of, well, we said h times f times e minus at. Okay, and what one first interesting property that we can see is that, as you remember, the Fourier transform is an isometry, and so it's also bijection, and it's in particular it's injective. So we're going to get the same ideas that the Laplace transform is also injective, which gives us one very interesting property is that the Laplace transform of some function is in particular equal to 0, means that your function was actually equal to 0. Well, you know that it's almost everywhere as usual. Okay, so next video we're going to study more in details all the properties, well, we're going to list quickly all the properties of the Laplace transform.